everyone, this is Srishti Joshi Thakur and welcome back to Girl Up Coders. Today we are going to start with one of the most popular topics for interview, that is graphs. And yes, so to start with, I would like to ask you all, what is exactly graph? So graph is what? So, like in computer science, a graph is a collection of nodes that is known as vertices, and the connection between them, that is called the edges. This is the edges, this is the vertices. So think of a graph as a network where each node represents an object and each edge represents the relationship between the two objects. So graphs are everywhere. Also in the real world, there are plenty of examples, like the social network, that is, like if you imagine a person as a node and each friendship is an edge, like on Facebook or LinkedIn or any other social media platform, they use graphs to model and analyze the connection between them. So we also use maps for navigation, like the Google Maps or any other map. So the cities can be represented as nodes, like I am here in Mumbai and you are in Kolkata, and we are connected by a highway, that is the edge, and our cities are the nodes. So the Google Map that we use also uses the map algorithm, the graph algorithm. So they find out the shortest path between the two cities through graphs. And also in the recommendation systems, when Netflix suggests movies, it uses a graph where nodes represent users and movies, and the edges represent the user preferences and rating. So if the rating is high, it would recommend that movie to that particular user, and also according to their preferences. And also in biology, if we say, like in biological networks, the graphs are used to model relationship between genes, and also in proteins and many other entities like chromosomes and whatever. Yeah. So now let us break down the basic components of graphs. So what is vertices? That is the nodes. Vertices or nodes so these are the fundamental units of graph. And also in our earlier examples, we were using people as vertex or a city or movie, and next was edge. So what is an edge? These are the connection between the vertices. Alright. So an edge can be directed or undirected. So what is a directed edge? Directed edge is where the connection has a direction. So for for example, if there is an edge between a vertex A and a vertex B, but not the other way down, like not from A to B, not from B to A, just from A to B. So it is a one-way street, like you can go from there to there, but can't come back. So this is a directed graph. But in case of undirected graph, the direction is two-way. So this is bidirectional. One can go from A to B as well as from B to A. So the edges might also have weights, and that could represent the strength of the connection, the distance, and any other relevant metric. So this can have a weight or a direction or distance or anything. So let us draw something. Let us take an example. So this is a node A. Then there is node B. Then there is node C. Then there is node D. Then there is node A. So this is an undirected graph with 4 nodes A, B, C, D, and their edges are this, and each of the edges are bidirectional. Like A can go to B, B can go to A, B can go to C, and C can go to B, C can go to D, and B can come back to C, B can go to A, and A can come back to D. So let's make a directed graph now. So here, if we are making A and B, and there are arrows, so this means that it is a directed graph, and it doesn't imply that a connection is from B to A unless there is another arrow in that direction. So if I am putting a directed arrow in a directed graph from A to B, and that is not coming back from B to A, then this is a direct graph. So now let us add few weight to this graph. So in this edge I can add, let's say 5 here. Is 5, next is 3. So the structures and properties of these graphs helps us choose the right algorithm to analyze and manipulate them. So these weights of the edges represent the direction, like the distance between the two vertices. So between the vertices A and B, the distance is 5. From B to C, the distance is 3, and so on. So we can also categorize the graphs. So this is a graph, and we can categorize them into different types based on their properties. So let us explore this. First one is the directed versus undirected. Directed versus um, undirected. So what happens in case of directed graph? The edges have direction and like a one-way street or anything. And in case of undirected graph, the edges have no direction. So they can be a two-way street also. Like a two-way street, how one can go from one direction to another. One can come back from that direction to that direction itself. Like that, the undirected graph works. And in case of directed graph, direction is specified like from A to B, then they can only go from that direction to that direction. Next was weighted and unweighted. Weighted graph versus undirected or unweighted. So what happens in case of weighted graph is that we assign a particular weight or cost to each edge, which could represent a distance, time, or any other metric. So also in case of unweighted graph, all the edges are treated equally, that is they have the same weight. We are not specifying any particular cost or anything. Next is cyclic and acyclic. Cyclic graph and acyclic. So in case of cyclic graph, it contains at least one cycle or a path that starts and ends at the same point. And in case of acyclic graph, there are no cycles. So this is a special type of there is a special type of acyclic graph, that is a tree which is connected and has no cycles. So a cyclic graph has at least one cycle and the paths start and end at the same vertex. And in case of acyclic, there is no cycle and there is a special type of acyclic graph, that is a tree, and that is very connected and has no cycle. Next is connected and disconnected. Connected and disconnected. Graph. So what happens in case of connected and disconnected graph is a connected graph is a path between every pair of vertices, and a disconnected graph has at least one pair of vertices with no path connecting them. So that means that some vertices can't reach each other. And like understanding these types is very crucial for selecting the right algorithm for tasks like searching or shortest path finding or cycle detection, anything. So now let us talk about how we represent the graph in code. So there are many ways to represent a graph, and like in case of adjacency matrix, adjacency matrix. So what happens in case of adjacency matrix is that there is a 2D matrix like 2D array, 2D array, and there are cells like cells containing The first one is I, second one is J, and it indicates whether there is an edge from the vertex I to J. And like for a weight graph, let's say the cells would store the weight of the edge, and here the weight would be stored. Next is adjacency list. So what is the list? In adjacency list, what happens is like we are having an array of lists, and each vertex has a list that contains all the vertices. So there's a list that contains all the vertices and that is connected to each other, and this method is more space efficient for like sparse graphs where there are not many edges. And this is simply a list of all the edges in the graph where, like, let's see, in case of edge list, what happens? Like, this is a list of all the edges. List of edges in a graph. So here in each of the edges it is representing a pair or a tuple of vertices. And that is very useful for algorithms that need to process all the edges directly. So let's see that what the representation looks like. So let us imagine that we are having a graph and the vertices are ABC and the edges are from A to B, B to C, like that. So how would we be presenting this graph? Is like A and B and C. So in case of adjacency matrix, what would happen? Here the edges are what? A to B, B to C, and then C to A, like that. Like A, B, C. So here what is happening? We can specify a particular adjacency matrix for this. So what would be the adjacency matrix? A, B, C, and A, B, C, 0, 1, 1, 1, 0, 1, 1, 1, 0. So the rows and columns represent the vertices and this one, and one indicates edges between the corresponding vertices. So this is an undirected graph, so the matrix is symmetrical. And for the adjacency list, what is happening is we are going from A to A is containing B and C, that is the vertices, and B is containing A and C, and C is containing A and B. So each of the vertex is pointing to a list of neighbors that is represented through adjacency list. Next is you can, um, you can create a edge list for this. Edge list. So in this case, the edge list would be AB, A comma B, and B comma C, and C comma A. So here each of the tuples present an edge between the two vertices, and like different algorithms might be more efficient depending on the graph representation we are using. And now that we know how to represent graphs, we can also explore how we can traverse them. So the most used algorithm for graph traversal is all we know BFS and DFS. So what is BFS? So BFS explores graph level by level. We are starting from a given vertex and listing all its neighbors before moving on with the neighbors. So it's particularly useful for finding the shortest path in an unvaried graph. And next one was DFS. I can rename it. In case of DFS, what happens is that we can dive as deep as possible on one path before backtracking and exploring other paths. So this method is useful for exploring all the possible paths for the different cycles in a graph, and we can also have code for this. We also have a code like yarn. So what is happening in this code is we are doing a graph traversal, and we are having the number of vertices, and that's stored in the variable num vertices, and we are having a linked list and adjacency list representation here is given like this one, ADJ list, that's the adjacency list. And next is we are having a constructor that is graph traversal, and it is inputting, like it's getting the number of vertices that's stored in the variable num vertices, and inside this dot num vertices, that is storing the num vertices, that is the global variable, and the adjacency list is containing the linked list. It is creating the new linked list, and it's storing the value at that position of num vertices, and then we are traversing it. Now we are going to add an edge to the graph, and we are doing it by the function dot add that we have learned before in the video of lists. Next is we are doing the DFS traversal. So what is happening here is inside the function DFS we are getting the value b, and we are creating a boolean array. Inside that we are storing the value of whether it's like we are storing true or false of that array, that list num vertices. So we are traversing, and next is we are doing the BFS traversal of the vertices, that is storing from starting from B, and here we are forming a queue, and the visited is storing true, and we are adding the queue, the elements to the queue, and then we are checking that the queue is, until the queue is not empty, we are doing what? We are first dequeuing a vertex from the queue, and then we are processing the node. So then after that we are printing it, and we are getting all the adjacent vertices of the dequeued vertex B, and if an adjacent vertex has not been visited, then we are marking it visited and we are entering it. And this is the main function in which we are sending the values. So this is how it's working, and yeah, so these kind of functions can be used for traversing a graph, and we are also able to print out the nodes in order that is listed. So let us wrap it up and let us look at some of the powerful application of graphs, and that would be, I would say, first is shortest path finding. Like in case of digital algorithm, shortest path finding. Yeah, so what happens is like algorithms like Dijkstra and Bellman Fold help us find the shortest path between the nodes in a graph, and also for navigation or routing. And next is topological sorting. So this is used in scheduling problems where certain tasks need to be completed before others. So it's implied in project management tools and in compiler. And next is network flow. So the algorithms like port recursion help in finding the maximum flow in a network. So that is used in logistics and telecommunications, and also in social network analysis. Network analysis. What happens is we can use graph to analyze and visualize relationships like social network, identifying influences and communities and trends. Also in search engines like PageRank that is used by Google, is a graph-based algorithm that ranks web pages that is based on the importance by analyzing the link. So understanding this application not only shows us the relevance of the graph, but it also prepares us for real life scenarios where we can apply graph and make useful applications of it and make our task more easier. So that's all for today. Thank you for diving deep into graph with me, and that's all. Thanks so much.